Today we are going to learn the performance analysis of the algorithms in terms of time and space complexity. What is performance analysis? Usually when the algorithms are designed, then these algorithms has to be converted into program by following a programming language syntax, and the program is submitted to the computer system for execution. And once the program is correct and it is able to understand correctly, then we will give set of legal inputs to the program so that the program has to produce the desired output. So when the algorithm is converted into a program, and when it is given for computer system, and here I am giving some set of inputs, it has to produce the outputs. So in this process there is a need for computational resources that are utilized by the program. So the important computational resources we will consider when we are measuring the performance analysis, one is the CPU time and the other one is the system memory. Other one is the system memory. So these are the important computational resources we will consider to assess the performance of the algorithm. So basically the performance analysis can be divided into two major phases. The first one is called as performance analysis and the second one is called as performance measurement. Performance analysis is a machine independent process. So at the algorithm level, before converting the algorithm into program, we will estimate how many computational resources the algorithm required to run to completion. So that is the reason why this is called as performance estimation, and this is the priori analysis we are doing. And based on the computational resources we are using, the performance analysis can be categorized into two categories. One is called as time complexity, which is nothing but the amount of time the algorithm needs to run to completion. And similarly, space complexity is nothing but the amount of memory it needs the algorithm run to completion. So these are the two measures we are performing either in the performance analysis and either in performance measurement. And the other one is performance measurement. So in performance measurement we are having algorithm, and algorithm is converted into a program and program is given for execution, and the actual time that is taken by the program for execution and the actual memory space it requires is completely depending on the machine in which the program is running. So these two parameters are measured at the program level. So that is the reason why it is called as a posteriori analysis. So these are the two things: performance estimation and performance measurement. And let us see in detail how the space complexity and time complexity is being measured. So let us consider the space complexity. So space complexity is defined as S of P, which is equal to C plus SP of I, where I is the instance characteristics and C is the constant, and this is also called as a fixed space requirements. So this is independent of the characteristics of the inputs, and this is a constant part. So the constant part, like the space that is assigned to simple variables and fixed structure variables and constants, is considered as C. And next, coming to SP of I. So this SP of I is usually variable space requirements, SP of I, where I is the instance characteristics, and this depends on the size of the inputs we are having, and that is decided at the runtime rather than at the loading time. So for example, the array size, array of n we used to say. So array of, if it is array of one variable, I can say that 1 unit of memory is required. If array of n, where n is known at the runtime, so I can say that if array is of integer type, if it is integer type, if it is taking, let us consider 2 bytes of memory. So depending on array of n size, for example, if it is array of 10, then I require 2 bytes for each array variable into 10 variables. So I require 20 bytes of memory. So these type of characteristics are called as instance characteristics, and these are like number, value of the inputs associated with instance characteristics, and also the recursion, number of recursions we are having, and it also specified in terms of the formal and local parameters and return address. So this is how the space complexity is being generated. So consider an example. So simple performing the algorithm which is performing the simple arithmetic operations. So if you observe here, I am having 3 variables a, b, c, and hence, so the constant part s of p constant is equal to 3. So because I am having 3 variables, and here there is no instance characteristics, means whose value is known at the runtime, there is nothing like that, so hence it is 0. So the space complexity is nothing but a simple constant which might be 3. And let us consider another example for calculating the space complexity. So this is the iterative function to find out the sum of the numbers that is stored in an array. So here I am calling an algorithm. So sum of array, and n is the size of the array, and this is one variable. So 1 unit of memory for s, and for I is equal to 1, I is another variable, so 1 unit of memory, and n is another variable, and for which 1 unit of memory I require, and array of I. So this is depending on number of times the loop is being iterated. So the constant parts here is nothing but, so I is a constant part, and n is a constant part, and s is a constant part, and also so this three constants parts I am having, and n units are required for storing the array variable. So hence the instance part is n plus 3 constants part for I, n and s. In this way the space complexity can be calculated. So for the given iterative function, the space complexity might be greater than or equal to n plus 3. So here I am writing greater than or equal to because it is the estimation I am doing, performance estimation at the algorithm level. And I also have the space complexity for the algorithm which is written in terms of the recursive functions. So here I am writing recursive sum array variables, and n is the size of the array. If n is less than or equal to 0, if there are no numbers in the array, then I am returning 0 as a result, else return. So to the last number, again I am calling recursive sum of a comma n minus 1. So here whatever the call we are making for recursive sum, it requires at least 3 words. So what are the 3 words we are having is nothing but the value of n and the return address, and followed by a pointer to the return address. And the depth of the recursion is n plus 1. N plus 1 times we are calling n number of times for adding n values, and plus 1 for checking the last condition, false condition. So the recursion stack requires, so n plus 1 is the depth of the iteration, depth of the recursion, and in each recursion we require 3 variables. So hence the space complexity is greater than 3 into n plus 1. So this is how the space complexity can be calculated. Now let us move on to the other performance analysis metric, which is called as time complexity. So time complexity is the amount of computer time an algorithm needs to run to completion. So the complexity of the function can be represented in terms of f of n. So there are 3 types of time complexities. One is called as best case time complexity. So this is nothing but the minimum number of computations required to complete the algorithm execution. And average case time complexity is the average number of computations required, and worst case time complexity is the maximum number of computations required to complete the algorithm execution. So in most of the cases, so the analysis means that it is the analysis of the algorithms. For example, if you consider the algorithm is having some addition, some arithmetic operations like addition, subtraction, multiplication, division and so on. So here this n is indicating the number of additions, the time taken to complete n number of additions plus the time taken to complete n number of subtractions, time taken to complete n number of multiplication, time taken to complete n number of divisions and so on, and this forms the time complexity of that particular program. So here to compute the time complexities, basically we are having two different methods. One is called as by introducing a variable called as a count variable, and the other one is called as by introducing a tabular method in which a step per execution is being counted. So in this particular one, let us see the first method by using calculating the time complexity by using variable count. So in this, what do we do is nothing but, so we are counting the total number of steps, um, um, so that each step is contributing something to the algorithm, and followed by each step how many times it is being called for, and these number of times calls are being added up so that it will form the time complexity. So let us consider an algorithm. So the same algorithm, finding the sum of the array variables. So here I am having S is equal to 0 0.0 initially. So this is a useful program step because it contributes to the algorithm. So hence count is a global variable, so which is initialized to 0. So hence, because for S executing S is equal to 0 0.0, I require 1 unit of time. So count is equal to count plus 1. Now I am entering into the loop. So for I is equal to 1 to n. So for entering into the loop, I need to initialize I is equal to 1. So hence again the count value is being incremented by 1. And then A of I value is being added to S, and which in turn being assigned to S value. So this is a arithmetic operation and which includes assignment also, hence my count will be incremented by 1. So like this it will be repeated. And once after the for loop, the last time I need to check the false condition of the for loop. So hence the condition check count is equal to count plus 1. The one more increment of count value. And finally I am returning the result. So return S, hence the count will be again incremented by 1. So in each step of the for loop, the value of the count will be increased by actually two increments. So like this we are having n iterations of the for loop. So hence it is 2n increments. And of course out of the for loop I am having 3 increments of count value. So this one and this one. So hence, so the time complexity of this particular algorithm is 2n plus 3. Let us consider the tabular method. So time complexity in this tabular method is determined by using a table which includes the step per execution, and this is called as a program step. Program step is nothing but a meaningful statement that requires some amount of time to execute that particular statement. So and then for each program step we will calculate the frequency. So let us consider the algorithm sum, the same algorithm. So here step per execution, here I am just calling an algorithm which doesn't contribute to the result of the algorithm. So there is no program step execution here beginning, no program step execution, and the frequency is also 0, and the total steps will be 0 here. And here s is equal to 0. Here it is a program step because I am assigning a value to a variable, and the frequency is only one time, so hence total number of steps is one time. So total steps will be getting by multiplying s by e into frequency. And coming to for I is equal to 1 to n, so here step per execution is 1, but the frequency, this particular statement is being called for n plus 1 times, n times for true condition and plus 1 time for the false condition. So hence total steps required is n plus 1. And finally s is equal to s plus ei. So one program step here, and this would be repeated for n times. So 1 into n, it will be total steps n. And return s. So here I am returning the s value, the resultant value. So program step is 1, and frequency is also 1, and here total steps is 1. So hence the time complexity, if I am adding up all these total steps, I will be getting 2n plus 3. So this is the tabular method. Let us consider another example, recursive sum, uh, in which the time complexity is calculated both using count method and the tabular method. So here recursive sum, so if n is less than or equal to 0, then if there are no elements, then I am just returning 0. Else I am calling recursive sum of a comma n minus 1 by adding the last term every term. So if you observe here, so checking the condition of if statement, so hence it is a one program step, so count will be incremented by 1. So next returning 0 is also one program step, so hence count will be incremented by 1. Coming to else part, so we need to uh, uh, increment counter by 1, because whenever we are calling for one return value, so count will be incremented by 1. So let us try to calculate the time complexity for this. So time complexity of recursive sum of n numbers is equal to, if you observe, if n is equal to 0, then here there are two count statements I am using, this one and this one. So hence it is a constant, 1 plus 1 it is 2. If not, if n is greater than 0, even though I need to check whether it is n less than 0 or not, so followed by so that means count will be incremented by 1, and when it comes to else part, count will be incremented by 1. So one for true condition and one for false condition. So hence it is 2 plus recursive sum of I am calling n minus 1, a comma n minus 1. So the time taken for recursive sum of a comma n minus 1 is this one. So this is a this is a recursive relation, and this recursive relation has to be solved to get the time complexity. So in the similar way, I can use the tabular method also. So here for algorithm calling, the steps per execution is 0, and total steps is also 0. If you observe here, I'm maintaining the differentiation between n equals to 0 and n greater than 0, because it is a if then else, either of this will be executed. So if n less than or equal to 0, so this one will be executed, and also this one will be executed, either this one or this one. Next return 0 again. So this is one program step. So whenever n is greater than or equal to when is less than or equal to 0, it returns 0. So in these two cases, because it is the else part, these two values will be zeros. And else return, so in this the first true conditions will be zeros, and this will be called for frequency is one time, and here this is 1 plus x times, here x is indicating the depth of the recursion. So I can say that x is equal to The depth of the recursion is TR sum of n minus 1. So the time complexity will be whenever it is n equals to 0, it is 2. Whenever it is n equals to n is greater than 0, then it is 2 plus x, where x is the recursive sum of n minus 1. So in this way we can calculate both the space and time complexities. So as per this, you can try out the assignment questions. Calculate the time and space complexities, both time and space complexities for matrix addition, Fibonacci series, factorial of n, and selection sort. So this is the performance analysis. Please post if any queries are there. Thank you for watching.